welcome to Physics 12, Dynamics Lesson number 4, Hooke's Law. As you may remember from earlier physics classes, Hooke's Law is simply a restorative force of any spring or elastic. Any object that, once deformed, tries to restore back to its original shape has a restorative force that follows Hooke's law. The equation is found F equal to K delta X, where F of S is the spring force, K is the spring constant, and delta X is the change in position, or the distance the object travels from rest. Here, K is always a negative value. The reason why this is a negative value is because the force of the spring must always be opposite to the direction the spring has been moved. As a quick example, what is the spring constant of a spring that makes a 50 kilogram person seem like they weigh 400 newtons after it stretches 28 centimeters? Here, like in many other physics questions, it may be easy to start with a picture. In this situation, we have a person standing on the ground hanging from a spring. Here we know that the string has stretched 28 centimeters, that the person weighs 50 kilograms, and that the scale reads 400 newtons. So reorganizing everything that we know the mass is 50 kilograms. We know the scale reads 400 newtons, so this is their weight, or in other words, their normal force is equal to 400 newtons, and that the distance the spring has stretched is 28 centimeters, or in SI units is equal to 0.28 meters. Remember to change all values into SI units. Next, let's draw a free body diagram. Here we have our force of gravity pulling the person down. We also have our normal force pushing the person up through the scale, and we have our spring force also pulling the person up. In this question, the person is not moving, so we may assume the net force is equal to 0. Since the net force is equal to 0, we have our spring force pulling up plus our normal force also pulling up minus the force of our gravity pulling down. We wish to find the spring constant, which is inside the force of the spring, so we will solve for Fs. This gives us Fg minus Fn. Here we know the spring constant is K times delta X, and the force of gravity is mg minus our Fn, which is our apparent weight. Therefore, our spring constant is equal to mg minus Fn over delta X. Putting in the values that we know mass is equal to 50 kilograms, gravity is 9.8, minus our apparent weight is 400 newtons, divided by our delta X is 0.28. Now remember, in this situation, our delta X is pulling down. 0.28 must actually be negative 0.28. After calculating the numbers, you'll find you get negative 321.428. Or with correct sig figs, this is equal to minus 3.2 times 10 to the 2 newtons per meter. This is the idea of Hooke's law. Let's apply this idea in a couple of questions. In this situation, an elastic with a spring constant 23.2 newtons per meter is attached to a 25 kilogram box. When it is stretched out to 12.2 centimeters, the box begins to move. What is the coefficient of static friction of the box? As with every question, let's start by drawing a picture. Here in this situation, we have a box attached to an elastic. This spring is stretched out until the box begins to move. And we want to find what is the coefficient of the box. So let's begin by writing down everything we know. We know that the spring constant K is equal to minus 23.2 newtons per meter. Here we also know that the mass is 25.0 kilograms. The distance it is stretched out is 12.2 centimeters. Centimeters, you may notice, is not an SI unit, so we will convert it to 0.122 meters. Here the box begins to move, so we know our spring force is now equal to the force of friction, and we wish to find the coefficient of static friction. Here, as with all force questions, we can go into a free body diagram. We have our force of gravity pulling the box down, our normal force pushing the box up. We have our spring force pulling the box forward, and we have our friction force pushing the box backwards. We know this box begins to move, so this is at the point where the net force is now totally equal to 0, and it begins to move forward with a slight increase. At this point, we know that the normal force is equal to the gravitational force, and as we've seen before, the static friction. And as we wrote earlier, the spring force is equal to the force of friction. Next, putting together other equations that we know the force of friction is equal to mu Fn. Here, as we found above, we know that the force of friction is equal to the spring force and that the normal force is equal to the gravitational force. The spring force is K delta x and the gravitational force is mg. Solving for the coefficient of static friction, we find K delta x over mg. We now have the value we wish to find on the left, and the right is only full of stuff that we know. So now we can punch in the numbers. So now we can put in our numbers. We know K is 23.2. We know delta x is 0.122. We know the mass is 25. And we know gravity is 9.8. Putting these numbers together, we find that the coefficient of static friction in this case is 0.011552653. Or, with the correct significant figures, this is 0.0116. This can also be written as 1.16 times 10 to the minus 2. Our last question for this lesson involves inclines and elastics at the same time. A 25 kilogram box is on a ramp at 33 degrees and attached to a 22 centimeter elastic with spring constant 22 newtons per meter. The box slides down the ramp 12 centimeters before it stops. What was the coefficient of kinetic friction? Here, this question may seem complicated because there are a lot of components, but if we take everything one step at a time and we break it down into simple steps we know, this will become an easy question. First, as with all questions we have, start by drawing a picture. We have a ramp at 33 degrees. On this ramp, we have a 25 kilogram box. This box is attached to a spring with a spring constant of 22 newtons per meter. The box then slides down this ramp 12 centimeters before it finally comes to a stop. What was the coefficient of kinetic friction? After we understand the situation, we can begin writing down what we know. We know our mass is 25 kilograms. We also know that the angle is 33 degrees. We also know that the length of the spring is 22 centimeters, or 0.22 meters, and that the spring is stretched 12 centimeters before it is stopped, or 0.12 meters. We also know that the spring has a spring constant of 22 newtons per meter negative. We wish to find the coefficient of kinetic friction because this object was moving when it stopped. Here, at first glance, this seems like a very difficult question. We have the spring force, we have friction, and we also have gravity all acting on the same box. However, if you break down this question into smaller steps, this will seem very easy, just long. Our next step is to draw a free body diagram. Here we have our force of gravity pulling the object down. Since this box is sliding down the ramp and friction opposes our motion, we have friction pulling the object up. Also, because the spring is being stretched down the ramp, our spring force is also pulling up. We also have the ramp pushing on the box itself perpendicular to its surface in the normal force. Here this question may seem difficult because we have three forces on an angle, but instead of dividing these three components into x and y, it is easier to divide gravity into perpendicular and parallel components. Here we will have the perpendicular component of gravity and the parallel component of gravity. For some, this may be enough, but for others, you may want to do one more step. Instead of looking at this free body diagram in this direction, you may tilt your paper slightly on an angle and look at it in another way. If you rotate this free body diagram slightly, this becomes an easier question. Instead of using the traditional x and y axes, we will use perpendicular and parallel as our y and our x respectively. For this question, I will leave the free body diagram on an angle so it is understood easier. In this situation, the box is finally stopped, so this is the point where all the forces have finally balanced. In other words, our net force is equal to 0. Using this assumption, we can state that the normal force is equal to the perpendicular component of gravity, and the parallel component of gravity is equal to the force of friction and the spring force combined. Our next step here is to find the components of gravity. We had a 33-degree ramp with gravity pulling straight down. We are dividing the components into a perpendicular and parallel component. Using our knowledge of trigonometry, we know this angle is 90 minus 33, and this angle is 90 minus the answer there, which gives us back to 33 degrees. After also tilting this situation, we can see that the force of gravity here can be broken down into its components, the perpendicular component and the parallel component with 33 degrees. So here we can see the perpendicular component of gravity is the force of gravity times cosine 33, and the parallel component of gravity is the total force of gravity times sine 33. We can now start putting numbers into equations and simplifying them. Our normal force is equal to the perpendicular component of gravity, Fg cos 33. The parallel component, Fg sine 33, is equal to the friction force, which is mu Fn, plus the spring force, K delta x. Combining these two equations, we find Fg sine 33 equals mu Fg cos 33 plus Kx. Solving for the coefficient of friction, we find mu is equal to Fg sine 33 minus Kx over Fg cosine 33. Now remember here that although K is negative, so is our X. So this total number should be positive. So this we should be minusing in the end. We also know that Fg is equal to mg. And putting those numbers in, we can find 25 times 9.8 times sine 33 minus K times X divided by 25 times G times cosine the angle will give us our mu. Here, notice for X, we used our change in our X. The actual size of the original elastic has nothing to do with the total force in the end, only the change in your position. Calculating these numbers together and remembering our sig figs, we have 0.64 as our final answer. That's all for the Hooke's law. Thank you for watching.